screen. Okay. Screen is visible? Theory?
Yeah. All right, I can see. Ideal diode, basic.
Okay. Diode. Okay. So last class, what we have seen, right? So just a minute, let me. Okay. So last class we have discussed, right? What is a random motion, right? In a semiconductor. So in equilibrium, the carriers after generation, they move very randomly, right? So you understood when they are in random motion, then the net motion is zero, right? Right? Theory?
Yes, sir. Yes, sir.
And also you understood what do you mean by no net motion equal to zero, right? So you understood that how to appreciate even if the carriers are moving so fast, how the net motion equal to zero. That you understood it. So for that we have used two tools. One is called ensemble average, right? Another is called time average. So both should be zero. Also another thing is you see across any plane the number of carriers moving from left to right equal to the number of carriers moving from right to left. That's right.
Right, sir.
And then using a one-dimensional picture, we have explained you how the net flux is number of carriers passing the unit area for unit time, right? The number of carriers passing the unit area per unit time is zero in equilibrium. So the flux from left to right is given by this P into Vth by 2. The flux from right to left also P into Vth by 2. So at equilibrium, the net flux is equal to 0. Right? Individually, they are very high. Right? Individually, the flux are very high. They are very high. Right? Individually, they are very high. But in totality, they are 0. Right? Right. Okay. And then last time we have explained you how if you go to non-equilibrium cases, in non-equilibrium, the net flux is generating. One thing is diffusion when the concentration difference is there. Another thing is called drift when the velocity difference is there. Okay. So today we will go through each of them and understand what is, right? So,
Right.
okay. First thing we will understood that is called drift. Drift. Okay. For that, let us consider a one-dimensional semiconductor. Getting? Sherry? So
Yes.
let us take the same like we have taken last time. We taken two person. Okay. They are separated by LC. Okay. Okay. The distance here is LC. Here also the distance is LC. Right?
Right.
Here. Okay. Now, what happens? The net flux is equal to 0. Right? Then you will apply a external electric field. Okay. Okay. So if I apply a external electric field, what it will do? This is region 1, this is region 2. Okay. What it will do? Right? This external electric field, right? External electric field support the motion from left to right, right, and it is oppose the motion from right to left. Clear? Clear? When I apply a external electric field, I will be entering into what? Non-equilibrium, right? What is non-equilibrium? Any external factor other than temperature. Clear? So
Clear.
when I put a electric field, what will happen? It will support the motion of carrier from region 1 to region 2, and it will oppose the motion of carrier from region 2 to region 1, right or not?
Right.
So the flux from left to right will increase and the flux from right to left will decrease, right or not?
Right.
Right, because flux is nothing but concentration into VTH by 2. Okay, so since when I apply electric field, the velocity of the carrier moving from left to right will increase, the velocity of carrier from moving from right to left will decrease. Clear?
Clear.
So net flux will increase from left to right, and the net flux will decrease for the carriers moving from right to left, because the electric field is opposing their motion, right? So if you see F net, right, F net, F flux from left to right minus flux from right to left. Okay, what will happen? They will not be equal because it is opposing the force from flux from right to left. It is supporting the flux from left to right. So there will be imbalance. Okay, and there will be net flux. Okay, and this net flux will go on increasing until the time this flux from left to right will become 0, right? So this cannot go increasing. If you go on increasing the electric field, right, this cannot go on increasing infinitely, because after a certain time, what will happen? This go on decreasing, this will be approximately 0, right? So after that, the net flux will be only the flux moving from left to right, right? So the electric flux will go on increasing when I increase the electric field. After a certain time, after a certain electric field, what will happen? The net flux will saturate. Clear? Then the flux from right to left will be approximately very small or 0, you can say, right?
Right.
Right. So there will be net flux generation whenever I apply a electric field. Okay. So then we'll understand one more thing, something called quasi-equilibrium transport. See, before the electric field, the semiconductor is in equilibrium, right or not?
Right.
For the electric field, the semiconductor was in equilibrium. When I apply electric field, right, the equilibrium will be disturbed. Okay, but it will not be disturbed so much. Okay, so I am disturbing the equilibrium by the external applied field, but I am not disturbing very much. Okay.
Okay.
Getting? So what is the meaning of this? Meaning is we are disturbing the equilibrium by a small amount. That is called quasi-equilibrium. Equilibrium transport. Getting?
Okay.
So what the meaning of this is? The net flux will be F1. So flux from, let us the flux from left to right I take F1. Okay. The flux from right to left I take F. Okay. Here. So it will be F1 minus F2. Right.
Right.
Net flux. Okay. This is the net flux. So I'll get some net flux, but the net flux will be very less compared to either F1 or F2. Clear? This is the first meaning of quasi-equilibrium. Are you getting? So I will get a net flux, but they are individually very less compared to F1 and F2. Let me give you one example. Suppose F1 is equal to at equilibrium. Okay. At equilibrium, suppose F1 equal to 1000, 10,000. Okay. 10,000 particles per second. Okay.
Okay.
Per second. Similarly, F2 equal to 10,000 per second. Okay. Now, when I disturb the equilibrium, right, this is in the equilibrium. When I go to quasi-equilibrium, right, quasi-equilibrium, or when I apply electric field, I'll get net flux. F1 may become 10,000 5. F2 may become 9995. Okay, so if you see F1 minus F2, F1 minus F2 will be 10. Clear?
Clear.
Clear. So 10 minus 10. And the F1 minus F2 is very less compared to either F1 and F2, right or not?
Right.
So this is the meaning of quasi equilibrium. Means I am disturbing the equilibrium little amount, but I am getting the net flux. And so net flux is very less compared to F1 or F2. That is the meaning of first one. Okay. Second thing is the random velocities, right? The random mean path, the mean free time, okay, the BTH, the random thermal velocity, all are almost same as in equilibrium. Okay, almost, not exactly, almost same as in equilibrium. In equilibrium. Okay. So with these two assumptions, we will now derive what is the net amount of flux after I put a electric field. Okay. So if I want to copy this thing, copy. Okay. So let's now derive the okay. Now derive when I apply electric field. Okay. The assumption is the net flux is very small compared to F1 and F2, and the all the equilibrium velocity, the mean free time, and all things are very little disturbed. Okay. So let's take a semiconductor. Okay. This semiconductor. Okay. Here. Okay. So this is including electric field. Okay. So what is drift? Okay. Drift means you see, since my electric field, right, is supporting the movement from left to right or not?
Right.
Right. So in the electric field, what is the average velocity of all the particle that is moving from this region 1? Okay. So we know the F1 is P into V1 by 2, right? Then the concentration is P into V1 by 2. As last class I discussed. Okay.
Okay.
And V1 is what? V1 is nothing but V1 is nothing but average velocity okay, of all the particle moving from left to right. Okay. So
Right.
you see, we have taken a distance LC, right? So whatever carriers are there in the distance LC, they will half of them will move to right, half of them will move to left in equilibrium, right or not?
Right.
Right. So now what will happen? What will be the velocity, average velocity of the carriers? They are moving from region 1 to region 2. Okay. Suppose see there is a carrier just next to here. Okay, this here. Okay. What it will do? It will move a distance of LC, right? Then it will cross this. Right or not? Before crossing this, this carrier, if suppose carrier is here, okay, it will move a distance how much? LC na?
Right.
To cross this boundary. Huh?
Yes.
So the carrier which are here, they will gain velocity against the electric field, right? So what is the velocity of this? We know from mechanics, right? If there is acceleration, right? Since there is electric field, there is a force, there is a acceleration. Okay. Suppose the velocity here is VTH. Okay. Because just the carrier is getting collided here. Just from here they have started, right? So they have a thermal velocity VTH, right? After generation, they have a velocity of after the generation, they have a velocity VTH, right or not?
Right.
After it generated, then it will moving towards the right. Okay. So at this point, what is the velocity? Velocity will be V1 equal to, sorry, V is equal to, V is equal to, V is equal to, okay.
Like
So what I'm telling, the average velocity of the particles, right, moving from left to right. Okay, so whenever a particle just after generation, it will start from this point, it will try to reach here. Okay, so what is the velocity gained by this particle after it reach travel a distance LC? Okay, so whenever a particle travel a distance LC, okay, and reach here, what is the velocity gained by that particle? That is my question. Getting?
Okay.
Okay, so that will be the initial velocity root over of, so we know v final square is equal to root over of v initial square plus 2 into acceleration into LC. Right? This is your simple mathematics, right? Simple mechanics, right? Not? So this is my initial velocity. This is my final velocity. This is my initial velocity. This is the acceleration against the field, right? So when it travels a distance LC, it is the velocity at this point. Clear to you? Theory? Hello, Siri?
Yes, sir. Audible, sir. It's v square minus u square is equal to 2a. That's
Yeah. Same. So v square is the initial velocity here. Then it crosses a distance LC against the electric field. So it get an acceleration. Okay, getting?
yes.
Okay. So this is understood. Okay, and we have an assumption, right? So let me take a common VT square common we can take. Okay. So if I take VT square common, so VT will come common. So we take VTH square common. So we'll get VTH into root over of 1 plus 2a LC divided by VTH square, right? And since what we assumed is the velocity is not changing much, right? So whatever is increment in velocity, right, that is very negligible, right or not? So what I am assuming, this is the increment in velocity, right? So because of Quasi equilibrium, okay, 2a LC is very less compared to VTH square, right? Theory? Hello?
Hello.
Yeah, is it right?
2a LC is very much less than VT square.
Because see, this is the amount of voltage velocity gained. But what you understood from Quasi equilibrium, whatever the gain, right, there is a very small change in velocity, right? So
Yes.
whatever change is there, that is very small. Okay.
Sure.
And we know root over of 1 plus x, if x is very small, it is equal to 1 plus x by 2. Clear?
Okay.
Yeah. Similarly here, I will do the same thing. So VTH into 1 plus x is here. Okay. 2a LC divided by VTH square into 1 by 2. Okay. This is the formula I applied here. Getting? Equal to VTH plus 2 get cancelled. LC into acceleration by VTH. Clear? Here. And we know VTH is equal to LC by tau C. Clear? So it will equal to VTH plus acceleration into tau C. Because LC by VTH is equal to tau C. Right?
Right.
So this is the velocity gained by a particle if it move from this point to this point. Okay? Okay. So let's suppose this will be V. Okay. So suppose okay, this much. Okay. And suppose there is another particle, okay, which is just about just here. Okay, just here. Okay. Then if you want to cross, what is the velocity when it is crossing? How much it will gain? Just beside the boundary. If you want to cross, while crossing, what is the velocity?
Sorry, sir.
See, so this V is the velocity of a particle when it started from here and just at the point of crossing, it is the velocity is VTH plus 8 tau, right? So suppose there is another particle who just besides the boundary. If you want to cross the boundary, what is the velocity?
Again, LC has traveled.
No, not LC. I'm telling you have to just cross this boundary, right? I'm just calculating the average velocity in region 1. So it will not gain, right? Because it is just neighbor of the boundary, so it won't gain any velocity. So it will be VTH only,
Okay, sure.
right? So that this particular velocity will be only VTH, right or not? Because
Right.
it just neighbor the boundary, so it won't gain any velocity while it is crossing, right? So
Right.
so this particular will gain maximum velocity. This particular will gain minimum velocity. So if I want to calculate the average velocity of particle from region 1, what I will do? Maximum plus minimum by 2. So what I will do? V1 is the average velocity from region 1 will be, maximum will be VTS plus A by 8 tau. 8 tau. Minimum will be
BT.
8 tau. Sorry. So what is V1 average? It is the average velocity of all the particles. They are traveling from region 1 to region 2. Okay, this is region 2. Right? So maximum is VTH plus 8 tau plus minimum is VTH divided by 2. So it will give me the approximately average velocity of all the particles, right?
Right.
So it will be VTH plus 8 tau by 2. Is this clear?
Clear.
In a similar way, since whatever particle from region 2, okay, they are want to travel to region 1, the electric field is opposing, right or not?
Right.
So what is the average velocity? It should be similarly, since it is supporting the VTH plus, when the V2 is the average velocity of the particle, they want to move from region 2 to region 1, crossing this boundary will be, how much will be? VTH minus 8 over 2, because it is opposite. Okay? Clear? So now, what is the net flux? Net flux will be F net will be equal to P into V1 is the velocity, average velocity of all particles moving from region 1 to region 2, minus V2 is the average velocity of all the particles. They want to move from region 2 to region 1 by 2. Right? This is the net flux. Okay? Hello? Hello?
Yes, sir. Yes, sir.
That's right. This expression is clear?
Actually,
Yeah.
here why are you using? Oh, okay. It's clear. It's clear.
This
That
is net
formula.
flux. Okay, this is net flux. Okay.
Okay.
So
Sure.
V1 minus V2 by 2. So V1 minus what is V2? V2 is VTH minus 8 tau, right? So means VTH plus 8 tau, right? Divided by, not divided by, right?
Right.
That's right. That's all. 8 tau by 2 minus 8 tau by 2. So 8 tau by 2, this is 8 tau by 2. Okay. This have to be kept cancelled. There's nothing, no by here. Okay.
Yes.
So this is my velocity. This is my net flux. Okay. Equal to P by tau into acceleration into tau, right? Tau c. Is it clear? Hello?
Clear.
Yeah.
Clear.
This is the average number of carriers moving per unit area per unit time, right? This is the average number of carriers moving from 1 to 2, right? For unit area or unit time. I don't know.
Yes, sir.
Yeah. So then if I want to calculate the current, right, is nothing but number of carriers into charge, number of carriers moving per time. So that is dq by dt. Current is nothing but dq by dt, right? Dq by dt. Right or not? So this is the number of charge carriers moving per time into charge. That will give me the drift current, right? So the drift current is nothing but current per unit area will be equal to Q into net flux. Okay. So this is the number of charge carrier per unit time into charge. Right?
Okay.
So it will be how much now? It will be equal to Q into F net is nothing but V into acceleration into tau c by 2, right? And we know
Right.
what is acceleration? Acceleration is nothing but now force is the Q into force is nothing but charge into electric field, right? Force by the effective mass of the holes. I am just talking about P type. Okay, since I am talking about only P type semiconductor, this is P type semiconductor. I am talking about only holes. Okay, now okay, so it will be this is the force for mass is the acceleration.
Okay.
Okay, so I will put this here. Okay, I will put it here. Hold on. U into P by 2 to tau c into what is the acceleration? Acceleration is nothing but Q into electric field by effective mass. Okay, this is my
Okay.
drift current. Okay, so if I want to just rearrange this one, how much I will get? So if you want to rearrange this one, okay, how much you will get? Rearrange Z drift equal to okay Q into P into Q tau c by 2 MP into electric field. Okay, let me write it down clearly. Okay, this is the expression, right? This is clear. I'm just rearrange this one. Okay, so now if I want to write it, J drift equal to okay charge into the whole concentration into Q tau c by 2 into effective mass, right, into
Right.
electric field. Okay, this quantity okay is called mu for mobility. Clear? Okay, so mobility nothing but how smoothly a carrier moves inside the semiconductor, because its tau c is nothing but the average time between two collision, right?
Yes.
Right? MP is the effective mass. So the more the mass, it will find difficult to move,
Right.
and the more the collision, the tau c is more. So if the more the collision, then it will find difficult to move. So the mobility contains how smoothly a carrier moves inside the conductor, right? So my drift current depend upon my concentration. Mobility is nothing but inside semiconductor how it moves smoothly. This tau c is nothing but collision time, right? So if it collide more, then the tau c will be more and the mobility will be less. Sorry. If tau c is less, right? Well, tau c less means it will have more number of collision. I don't know.
Yeah,
Hello?
actually,
Yeah. Tell me.
yes, for less time, more number of collision.
So for left time motor collision, so mobility will reduce. It will find difficult to move. I don't know. Hello.
Right.
So I'm telling the mobility will discuss extensively. Okay. So more the collision, less is the tau c, less is the mobility.
Yeah.
Yeah. So this factor is called mobility. Okay, will depend upon the collision time and effective mass. That's what you don't understand now. And now later we'll see how this tau c depend upon many factors.
Okay. Actually, this mobility shows the smoothness, right, sir? So, uh, if how smooth it moves, that means less number of collisions it should happen, right, sir?
It means if you want to move smoothly, you should have less number of collision.
Okay.
Getting?
Clear.
Yeah. So this is my drift velocity. This is called mobility. Okay. Mobility mu is equal to charge into tau c by 2 into effective mass. Okay. This is effective mass. Okay. So more on this mobility we will discuss later. But now understood that a drift current will depend upon the external electric field, also the concentration, also the mobility. Okay. This is my drift current. The current is due to the external applied electric field. Okay. So now we'll go to diffusion. So we'll go to diffusion transport. Okay.
One second, sir. Can I see the last slide? Just
Yeah.
take a note. Okay. Thank you.
So now you understood because of the applied electric field, it have created a current that is called drift current. Okay. Then we will understand diffusion current. Okay. Diffusion means whenever there will be a concentration gradient, right, we will get current. Okay. So suppose take a semiconductor. Okay, this semiconductor. So same thing you will do in region. Okay. Suppose in this, okay, this is my region 1. Okay. Sorry. This is region 1. This is region 2. Okay. So now 1 and 2. Okay. So then we know what is the net flux. Suppose there is a, we want to plot the concentration versus distance. Okay. Suppose this is my concentration. Okay. This is the distance. Okay. This is my semiconductor. Suppose the concentration is varying somewhat like this. Okay. Let me make one. Suppose I'm approximately there is like a straight line. Okay. This is the variation of concentration across this semiconductor. Okay. So now in this case, I want to find out what is the net flux across this observation plane. Okay. This is my observation plane. What is the net flux? Okay. So we know, and the net flux is how much? You know, the net flux will be equal to, right, P1 minus P2 into VTS divided by 2. Right? Right. Okay. Suppose P1 is the average concentration in region 1. Okay. So the region 1 concentration is vary. Okay. Suppose at this midpoint. Okay. At this midpoint. Okay. Let the concentration is P1. Okay. At this midpoint, the concentration is P1. Right. Suppose at this midpoint, the concentration is P2. Okay. Hello. Suppose this is P2. Okay. So I can say the average concentration in region 1 is P1, right? Because there are half of the time the concentration is more than P1. The half of the distance the concentration is less than P1. Okay. Exactly. So exactly in the mid I will get the average concentration. Clear? Similarly here half of the distance concentration is more than P2. Half of the distance concentration is more than less than P2. So the average concentration is P2 only. Okay. Say this is P2. Okay. So this is suppose what is the slope of this? Okay. Slope of this is how much? This is suppose the distance is the distance is LC, right? Because I'm taking half of the thing. So are you getting?
Yes. Sir.
See, the concentration in region, average concentration in region P1, and region 2 is P2. Okay. If I want to take the slope means P1 minus P2, by distance is LC only, right?
Right.
Because I'm taking exactly at a midpoint, Okay. Midpoint to midpoint, this is LC only distance. Okay. So what is P1 minus P2? P1 minus P2 by LC is the slope.
Actually, it's a negative, right, sir? P2
Yeah.
minus P1.
No. So P1 minus P2 by LC, okay, will be giving me slope of this is minus dp by dx. Okay, slope is negative, na?
Okay.
Slope is minus dp by dx. Clear? So since the slope is negative, negative slope is given by p1 minus p2 by lc. Okay.
Okay.
Okay. So now what I have to do? I have to put all the things here. But net flux? Net flux is p1 minus p2 is lc into minus dp by dx into vth. Okay. Minus lc into, okay, dp by dx by 2 into vth. Okay, is equal to minus lc into vth by 2 into d by dx. Okay, this is my net flux, right? So there is a net flux because of concentration gradient. What is the meaning? Because the holes since they are more in region 1, okay, because of the concentration gradient, naturally they will try to move to region 2. Okay, that's why we will get some current or net flux. Net flux is generated because the concentration in region 1 is more compared to the concentration in region 2. Okay, that's why they want to flow from region 1 to region 2. So we get a net flux. Clear to you?
Clear.
Yeah. Okay. So this is my net flux. Okay. So if I get a net current, what I have to do? Net current, J diffusion equal to Q into net flux. Okay. Because number of particles moving per time into charge. Okay. So it will be equal to minus Q into LC into VTH by 2 into dp by dx. Okay. So this is called a diffusion current. Okay. So diffusion current equal to minus Q LC VTH by 2 into dp by dx. Okay. This LC and VTH by 2 is called diffusion constant. Okay. Equal to minus Q into diffusion constant dp into dp by dx. Okay. So this is called diffusion coefficient. Okay. This dp is called okay. So it decides like what should be the it depends upon the semiconductor, right? So for different semiconductor, it will be different. Right or not?
Right.
Clear?
Clear, sir.
Okay. So now you understood that. So if I want to summarize, I got J drift is equal to minus Q, okay, into mobility into concentration into electric field, right? You got that. Q into P into mobility into electric field, okay. So J diffusion equal to minus Q into dp into dp by dx, okay. So drift current depend upon the external electric field. Is nothing but my this is nothing but the electric field, nothing but potential gradient, right? Potential gradient, okay. D v by dx, okay. So the drift current depend upon the gradient of potential, nothing but electric field. Diffusion current depend upon the gradient of concentration, nothing but dp by dx. Clear to you?
Very much clear.
Okay. So now we will try to get a link between mu p and dp. Okay. This will be coming in the examination. Okay. So we'll try to get a link between dp and mu p. Okay. So what is dp? Mu p is equal to, okay, q into tau c by 2 mp. dp is equal to lc into vth by 2. Okay. So now dp by mu p, okay, is equal to lc vth by 2 by q tau c by 2 mt, right? So it will be equal to half half got cancel. Okay, will equal to MP by Q into VTH into LC by tau c. Right? What is LC by tau c? Theory. Nothing but average collision distance by average collision time is equal to what? Thermal velocity, na? Hello? The average collision distance, what I'm telling, the average collision distance by average collision time equal to is equal to what? Is equal to the thermal velocity. This one.
It's a like
Thermal velocity, right? So thermal
VTH.
velocity, nothing but getting that?
VTH itself.
Yeah, exactly. VTH into this is also VTH. Okay, so I got MP into VTH square by Q, right? This is nothing but your dP by mu p. Right? Okay.
Right.
So we know for a three-dimensional situation, right? Three-dimensional situation, we know the kinetic energy. Okay, just take it granted here. Kinetic energy is equal to 3 by 2 kT is equal to, okay, half mbth square. This is the kinetic energy. If you do the molecular gas theory, okay, it will come around 3 by 2 kT. Okay, this is from gas theory. Okay, and what is then mbth square? M Bth square is equal to, okay, half I got cancel 3 kT. Here, Sherry,
Yes, sir. Yes, sir.
I'm telling this is the average kinetic energy of a gas molecule. Okay, so if you compare this, the kinetic energy equal to half mbth square. Okay, so mbth square will come 3 kT. Okay,
Clear.
yeah. So then this is for three-dimensional cases. Okay, for one-dimensional case, what will happen? mbth square is equal to this divided by 3 equal to kT. Okay, so now dP by mu p equal to m/t square by q equal to kT by q. kT by q. Okay, this is nothing but thermal voltage. Okay, not this is not small vt only. Okay, this is called Einstein's relationship. Okay, so mobility and diffusion constant are interrelated. Okay, by a voltage called thermal voltage. This is called Einstein's relationship. Okay, this is very important for the exam. Okay, so if you know mobility, you can easily calculate diffusivity or diffusion constant.
Okay.
And this point is clear to you?
Clear.
Yeah. So now we will understand a
Yes,
little bit more about the mobility behavior. Okay, then we will end the chapter. Okay.
The value is 0.026. That value is kT by 2, right?
Yeah. At t is equal to 300K.
Okay. First time we were talking about the Boltzmann constant, that kT equal to 0.026.
Then KT by Q is around 0.026 volt at T is equal to 300K. Okay. If high temperature, it will be higher. Fine.
Fine.
Then we will understand something more about mobility. Okay. Then we can complete this chapter. Mobility behavior. Heard this. Okay. We know mobility equal to, okay, unit tau c by effective mass. I don't know. Okay. So what I'm telling, like we discussed, what are the things that is affecting my mobility? Okay.
Okay.
So the first thing is we call ionized impurity. Right? So whenever you take a p-type or n-type semiconductor, Okay, so when I suppose you take a n-type semiconductor, there are a lot of dopant atom. So after dopant atom is giving the electron to the conduction band, it is ionized to positive charge. Right? Similarly, in my p-type semiconductor, whenever a acceptor atom is accepting an electron, it is getting negative charge.
Right.
Okay, so these are the ionized impurity. They are there inside the semiconductor. So whenever a carrier is moving inside semiconductor, they will come across this ionized impurity. Okay, and they will get collision with this impurity. That is called ionized impurity scattering. Okay, so whenever a carrier moves inside the semiconductor, it comes across this ionized impurity. Okay, scatter means change the direction. Okay, this is called ionized impurity scattering. Okay, scattering means after the collision, it will change the direction of motion.
Right.
Okay, this is called ionized impurity scattering. There is something called lattice scattering. Lattice or phonon. Right, I told you. What do you mean by lattice scattering? Phonon scattering? See, whenever at temperature T greater than 0, okay, all the atoms are vibrating. Okay, so whenever my carrier is moving inside the crystal, it will come across the vibrating atom. Okay, it will collide with the vibrating atom. That is called lattice scattering. Here,
Clear.
okay. So inside the semiconductor, the carrier is majorly affected by these two phenomena. Okay, even though suppose there is electron, the electron may collide with electron may collide with hole. Okay, that is called carrier scattering. So whenever electron is moving around it, so it may collide with another free electron or another free hole. Okay, so that also there. That is called carrier scattering. Carrier scattering. Okay,
Okay.
but since these two are measure, okay, they contribute more to the mobility. So these two are only important thing, okay, in the semiconductor. So even though this is there, this is very negligible compared to these two, first and second. Okay, third one is this is negligible compared to first and second. Okay,
Okay.
so now we'll understand a little bit about ionized impurity scattering. Ionized impurity. Okay, what happens? You see, suppose there is a donor impurity, okay, donor impurity, Nd plus. Okay, Nd plus. Suppose a hole particle charge is moving like this. Okay, whenever it meets this rate, it will change the direction. I don't know.
Right.
Right. So the change in direction whenever it meets a ionized impurity is called ionized impurity scattering. Okay. So on what it depend? So the more it bend or the more it scatter depend upon the how much velocity. Suppose the more the time it come in contact with this Nd plus, right, it will scatter more. Okay. So what does it mean? The hole is moving around. Okay, when it come in contact with the Nd plus more time, it will scatter more. Okay, suppose it have very high velocity. The high velocity means it will spend only very less amount of time in the vicinity of this charge, so it will bend less. Okay, so this is nothing but suppose it will have again. So if it velocity again very less, it will scatter very less. Okay, because just a minute, it may sit down. Okay. Okay, so what I'm telling, the more the velocity of the carrier, right, it will come in contact, it will spend the vicinity of this particle very less amount of time,
Yes.
right or not?
Yes.
So
Right.
if it will come with more velocity, okay, so this is suppose v1, okay, so suppose it will come with v2, suppose I will take v2, okay, then it will scatter less na v2, okay, v2 is more compared to v1, okay, because it has very high velocity, it will spend very less time in contact with the Nd plus, so it will bend less, right? Suppose I take another velocity, suppose v3, v3, v3 even more than v2, okay, what will happen? Since it is very high velocity, right, it come with very high velocity, so it will spend very less time in contact with this Nd plus, so it will bend less, right?
Right.
Right. So what I'm telling, the extent of the scattering, the extent of change in the direction depend upon the velocity of the incoming carrier. Okay.
Okay.
So the extent of change in direction, okay, will depend upon the
Velocity.
velocity of carrier. Okay. Okay. Actually, it depend upon the amount of time it spends with the particle. Okay. Depend upon the amount of time. Time it spends in the vicinity of atom, impurity atom. Okay. Clear?
Yeah.
Yeah. Okay. So now the thing is, suppose if you go on increasing temperature, right? If I increase temperature, right? We know the random thermal velocity also will increase, VTH. I don't know.
Right.
Because if I increase temperature, that the thermal energy will be more, and the thermal velocity also will be more. I don't know.
Right.
So since thermal velocity will be more, what about the scattering, the impurity ionized scattering? It will less or more. Since if I increase temperature, the velocity is more, scattering will be more or less?
It will be less.
Less, right? So scattering will be less. Okay, means the tau c, right, will be more, right? Because it will collide when you increase the velocity. Okay, the scattering means the tau c will be more. Getting? Tau is nothing but every collision time. Okay, so collision time is a measure of the scattering.
So,
Okay.
we have told that the velocity is more, so the collision time will be less, right?
No. This collision time is because collision time is nothing but collision between not two particles. It is the collision time between this ionized impurity and this carrier. Okay, this time is talking about TCI. Okay, this is TCI. The collision time is okay. This is tau collision due to impurity. Okay,
Right.
only impurity I am considering. Okay, so I am telling the more the velocity, right, it will scatter less. Scatter less means the collision time also will be what? More.
Sir, actually, I cannot see the updated slide.
So I did not update anything. I'm just in the same slide. Can you see anything?
Yeah, now I can see.
So what I'm telling, see, the scattering due to ionized impurity, right? If you go to higher temperature, right, we will get the velocity will be more, right? Since the velocity will be more, scattering will be less, right?
Okay.
Scattering will be less. Less means what? Scattering means nothing but change in direction is less. Means what? The collision time is more, right? You see in the layman term, when I go to higher temperature, the velocity of particles is more. Okay, so they scatter less. The scatter less means definitely they collide less.
Yes.
So collide less means the collision time for the impurity ionization is more.
Okay.
Clear?
Clear.
Clear. So as I increase temperature, okay, the TCI will be more. So it is nothing but mobility rate. Mobility is nothing but proportional to TCI. Tau CI will be more, right? So the mobility will be improved. Because of the ionized scattering, you will go to high temperature. Remember, I am talking about only ionized impurity. Okay, so the mobility due to ionized impurity will be more if you go to high temperature. This statement is clear to you?
Clear, clear.
Clear. Similarly, if I have the concentration Nd plus, so if I increase the concentration, right, what will happen? Then the scattering will be more, right, because it will see the ionized particle more often because it will be more, right. So if I go on increasing the donor concentration, right, the ionized impurity scattering will be more or less. It will be more, right, because I have more number of charge in the more number of positively charged donor in the crystal or a positive charged bounded atom, or I can say if I have more the doping, right, the more the number of bounded atom, or the more the number of bounded atom, the more the scattering. Clear?
Clear, clear.
So the more the scattering means tau Ci will be reduced as Nd increase, right? Because when Nd increase, they will scatter more. Similarly, the collision time will be less. Okay.
Okay,
See, when I increase the concentration, they will scatter more. Scatter more means they will do more collision. More collision means that collision time because for the scattering will be decrease. Clear?
actually, that is the point where I'm getting some doubt. Like,
Yeah, please tell me what is doubt.
like we are spending more time on collision.
So
So that means
so I'm
scattering
telling,
will
if
be
I have more number of charges, okay, more number of charges, okay, what will happen? This particle will see more number of particles, right? So it will scatter more.
okay. That's okay.
So scatter more means mobility is less, na?
Yes, yes.
So that's what I'm telling. So this is forgot. This is temperature. I'm talking about first thing is about temperature. If I increase temperature, the velocity is high, so it won't find time to meet and it will just bend less. Okay, but if I have more number of carriers, then it will meet, right? So I'm telling, consider a case where I have less carriers. Second case, carriers are more. Definitely charge this hole will meet more number of this Nd plus, then scatter will be more, na?
Okay, okay, okay.
The second case is I am increasing the donor concentration. I am increasing the doping concentration.
Okay, okay.
Okay. So more the doping concentration, more the scattering, less the collision time. Right? So and also it will affect the mobility. Mobility will decrease. Right or not?
Right, sir, right.
So I am summarizing the impurity ionization scattering. So the scattering due to the impurity ionization. Okay. If I increase temperature for a particular doping concentration, if I increase the temperature, the velocity of the carriers will be more. They will spend less time in the vicinity of the bounded carrier, bounded atom. So the scattering will be less. Okay. And so if I increase temperature, VTH will be more, scattering will be less, and my mobility will improve. Mobility will be high. Okay. But
Okay, okay.
if I increase doping, the scattering will be more and mobility will be less. Okay. So, and it has been said the mobility due to ionized impurity, okay, proportional to temperature power of 3/2. This is not very accurate, but approximately it depends upon that. Okay, so if temperature increases, the mobility due to ionized impurity increases because the velocity increases and they spend less time, and the collision also less, the scattering is less. This is clear to you?
Yes.
Okay, this is nothing but my mobility impurity ionization scattering. Okay, what is another thing is called lattice scattering, right?
Let.
Lattice scattering. Okay. Well, lattice scattering, nothing but a vibrating atom, right? Atoms are vibrating. Okay. So when they are vibrating, right? So this, whenever a carrier meet a vibrating atom, they will scatter. Okay. So if I increase temperature, okay, if temperature increase, okay, what will happen? The atoms will vibrate more.
Okay.
So when they vibrate more, definitely the carrier will have more collision. Na? If you increase temperature, the lattice will vibrate. When they will vibrate, definitely the collision chances is more.
Yes. Yes.
Right? So the tau Ci will be reducing. Tau C, this is lattice scattering, this is Cl due to lattice scattering. Lattice scattering will reducing, right? Because if I increase temperature, the scattering due to lattice atoms, the atoms will vibrate more. When they vibrate more, they will scatter more. Scatter more means that the scattering time will decrease, so that the mobility also will decrease. Clear?
Clear.
Okay. So the mobility lattice scattering, okay, proportional to approximately temperature of minus 3/2. Okay. This is called scattering due to lattice vibration or phonon contention due to lattice vibration. Okay, this is vibration. Okay, lattice vibration. Okay, this is the lattice scattering. Okay.
Okay.
Okay. Suppose for tau Ci is the collision time for the ionized impurity scattering. Tau Cl is the collision time for the lattice scattering. Okay. So for tau Ci time, one collision is happening. Okay. So what is the collision per time? What is the number of collision per unit time? Okay. So the total number of collision is tau C. Okay. Suppose this is suppose tau C is the number of collision per one time. Okay. The tau C takes for one collision. Okay. So it take tau C for one collision. Okay. So for unit time, how much collision will be there? It will be one by tau C, na?
Yeah. Yes. Yes.
See, I need tau C time amount of time for one collision. For unit time, it will be one by tau C time number of collision. So one by tau C is the total number of collision per unit time will be equal to the number of collision due to the lattice scattering tau Cl plus the number of collision due to ionized impurity scattering. Right? So the total number of scattering is equal to number of scattering due to the impurity ionization scattering plus lattice scattering. Right?
Okay. And the other type of scattering can be negligible, right, sir?
Yeah, negligible. Yeah. This is the total. So this is the total number of collisions per unit time equal to total number of collision due to lattice scattering plus total number of collision due to impurity ionization scattering.
Okay.
Okay. And you know the tau C proportional mobility. So I can also write 1 by mobility equal to 1 by mobility due to impurity ionization plus 1 by mobility due to lattice scattering. Right?
Right.
Right. So also we know okay, I have to add a new page. Page is over. Yeah, tell me. Any doubt in that?
Once more, can I see that mobility formula?
Huh.
That earlier slide.
Huh. Which one?
Where we have derived that mobility formula.
This one? Here.
Just I have seen that.
Yeah, this one, huh?
Yes.
Huh. Tell me.
Okay. Okay. No, it's clear. That was
Here.
the
Okay.
effective mass in the.
By effective mass.
Okay.
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 Okay. Now understood. Lattice scattering is proportional to T by because when I increase temperature, the lattice vibrate more, so the mobility is less. Right? Similarly, we know the mobility due to ionized impurity scattering is proportional to T by 3/2 because if I increase temperature, they have more velocity, they will spend less time, and they will collide less, and scattering will be less. Clear?
Okay.
Okay. So if I want to plot the mobility versus temperature, it's a very important question for exam. Okay. Want to plot mobility. Okay. So the mobility versus temperature. Okay. So if I see lattice scattering, right, it is decreasing temperature, right? So it will like this. Right? This is mu L, right? I don't know.
Right.
What is the improved in it will increase with temperature, right? So it is this is mu I, right?
Right.
So if I want to find out what is the total mobility, right? So in this region, whichever is lower, that will contribute, right? Because you see, it's like two resistors in parallel. Okay. So if there are two resistors in parallel, okay, this is R1, this is R2. Okay. So whichever is lower, that will like account to my final mobility, right? Suppose R1 is 1K. Suppose R1 is 1K. Okay. So this is 1 mega. So what will be my total resistance? Total resistance are total. It will be near to 1K, na?
Yeah, less than the lowest resistance.
Yeah, less than. So similarly here it is like parallel combination, right? Parallel combination. So whichever is less, that will be dominate my total, right?
Okay, okay, okay.
Okay. So if I want to see the total, right, it will be whenever it is this is less in the below temperature range. Okay. So it will be like this. Okay. This is my total mobility, right? Okay. So in this range, lattice scattering is dominating. So mobility due to this is so, and lattice scattering is more. Sorry. The mobility of due to lattice scattering is more, but mobility due to impurity ion scattering is less. So which is less, that is dominating. So in this region, mu I is dominating, right? In this region, mu L is dominating. Clear?
Okay, okay.
So whichever is less, that is dominating. Clear?
Clear, sir.
Clear. So this is my total mobility curve. Okay. So now we'll see something else. So now is something called conductivity. Very important for exam. So we know Z drift is equal to how much? Q into mu P into concentration into electric field, right? I don't know.
Right.
We derived today.
Yes.
So in this term is called conductivity. Sigma into P. Okay. Now this is called conductivity. Okay. So what is sigma? So if you see in a semiconductor where both hole and electron will be there, right? Then both electron and hole will be there, right? What is sigma? Sigma will be equal to Q into mobility due to holes into concentration of holes into plus
Electric.
Q into not electric field, right? This sigma is Q mu P and P only, right? This is my
Oh,
sigma.
sigma. Okay.
Q into mobility due to electron into concentration due to electron. Okay? This is my mobility when both are there. Okay, suppose you take N type. For N type, N is very more compared to the concentration P, right? Then
Right.
sigma will be approximately equal to Q into mu N into N, right?
Negative sign is there.
No, there is no negative sign. This is single quantity is just a simple quantity. Okay, conductivity is nothing but how conductive my conductor is. Okay, like uh, how easy for the carrier to move, and nothing but how the current flows. Okay, so depending upon the electric field. Okay, if the conductor is more conductive, more is the current. If conductor is less conductive, it less is the current. Okay, getting?
Getting it. Getting it.
Yeah. So it is the like how the current flow, how much how the current flows, right? Depend upon the conductivity. Right. So then if I take okay, if I take intrinsic, right? Intrinsic silicon, right? So there where you know concentration of hole equal to concentration of electron equal to Ni, right? They are both are equal Ni, right or not?
Right.
Right. So it will be sigma equal to right Q into mu n into the concentration of electron is Ni plus Q into mu p into concentration of hole is also Ni only, right? Equal to Q into mu n plus mu p into Ni, right?
Right.
Right. So equal to, so if I take the proportional to this mobility proportional to 3 by 2, okay, into this Ni is proportional to how much? A into 3 by 2 into exponential of minus Eg by 2 kt, right? This is my intrinsic concentration proportional to, right? This is my mobility proportional to, I don't know.
Sir, mobility
Yes.
always it's 3/2.
Actually, mobility is proportional to just a minute, not 3 by 2. That is my mistake. G2 will be some t to the power of some alpha, some constant. Okay, getting?
Okay. Okay.
I don't.
Because
Okay.
of
Uh,
both the scattering, we
yeah.
have to
So
take
it
this.
depends upon which temperature range and which scattering is there. So I taken t by alpha. Okay.
Oh,
So
okay.
now what I'm telling, you would take log sigma I, right? Log sigma I. Okay. Will be proportional to how much? Will be equal to, okay, log sigma I proportional to, okay, this is 3 by 2 plus alpha log t plus minus Eg by 2 kt na, getting? This t 3 by 2 plus alpha I have taken common, okay, 3 by 2 taken, so it will be 3 by 2 plus alpha into log t. If I take a log,
Yes.
and log of exponential will be an Eg by 2 kt.
Yes.
Okay, so the log t is a very small dependence compared to direct proportional 1 by t. Okay, so if I plot log sigma I, okay,
Okay.
sigma I, okay, here I will plot 1 by temperature. Okay, this dependency is almost negligible compared to this dependency. So okay, if you see, if you see the slope, right, slope will be minus Eg by 2k. Clear?
Clear.
Clear. So in exam they will ask if what is the log sigma I versus 1 by t give, it give you the energy gap. Okay.
Okay.
Okay. So that's all about this transport. Okay. Or only one thing before leaving I want to tell you. There are some questions you can solve. Okay. One more thing I want to tell you before leaving. Okay. So we know, suppose you take n type. Okay, n type. What is conductivity? Conductivity equal to proportional equal to Q into mobility into the concentration. Right. So if you want to plot, right, you know Nn0 is proportional to in n type, right? It will be like this, like this, right? If I want to plot the concentration of electron in n type semiconductor, it is like this. I have three regions, right? Region 1, region 2, region 3.
Yes.
I have explained, right?
Yes.
Okay. Then then what is mobility? Mobility we know. Okay, across temperature it will be like this curve, right?
Right.
Right. Then what will be my conductivity? Across temperature it will be nothing but multiplication of this and this, right?
Right.
It will be multiplied by 2. Okay, so what I will get, if I want to plot sigma versus temperature, it will be, so in this range it will be almost similar. Okay, here it will be like this, here again it will be exponential like this. Ready? This is nothing but multiplication of this two. Clear?
Clear.
This is the sigma versus temperature curve. This is why I ask in the some good exams. Okay.
Okay.
So that's all about my transport chapter. Okay, where we discuss very clearly about what are the drift. Today we discuss what? Today we discuss what is the drift transport. Okay, drift transport we understood. When we apply electric field, there will be net flux. Okay, that is proportional to my external electric field mobility. Okay, nothing but electric field mobility and concentration. Right, this is the band drift. But diffusion depend upon my concentration gradient. Okay, so it is q dp by q dp by dx. So it depends upon the concentration gradient. It depends upon the external electric field. Okay, and then we discuss about mobility. So we know dp and mp relationship given by vt. It is called Einstein's relationship. Okay, then you understood about how mobility depend upon the ionized impurity and the lattice vibration. Right, this is the both things we discussed. Then we have discussed the conductivity. Okay, this is the final curve. All things is clear to you?
Clear.
Okay. So now we'll take some questions. Okay.
Okay.
So since people are less today, so we'll start diode freshly in the next class. Okay. We'll take some
Okay.
questions. Okay. Now slide visible.
Yes. Yes. 19.
Okay. Okay. Fine. Just a minute. Okay. In a p-type semiconductor. Okay. The question is, in a p-type semiconductor. Okay.
Okay.
The conductivity due to holes sigma p. Okay. Is what? Option A. Option A is concentration into charge divided by mobility. Option B is given mobility divided by concentration into charge. Option C is given by concentration into charge into mobility. Option D is given by 1 by concentration into charge into mobility. Which is right?
C.
C. Right? Very straightforward. Right? The conductivity of an intrinsic semiconductor, right, is given by 1 sigma is equal to E into Ni into mu n minus mu p 2 sigma is equal to E into Ni into mu n plus mu p
Right, sir.
3. Yeah, this is right, right?
Right.
Equal to
Second.
Ni into mu n plus mu p. So it should be right. It's very straightforward, right? This is the kind of question you will get. Okay, very easy. If you understand the thing, it's very easy, right?
Yes, sir. Yes.
Next slide. Next slide is not coming. Nothing to this. Could you see?
Overlapping.
No, don't know why it is available. Okay, we'll see. Now it's moving. Okay, this is complete. So we'll take a eraser. This is a big eraser. Go to this. Good. Don't know how it come. Okay. Okay. So by increasing temperature, okay, the electrical conductivity would increase in metal as well as intrinsic semiconductor. Increase in metal, decrease in intrinsic semiconductor, decrease in metal, increase in intrinsic. Which will be right?
C.
C na?
C.
And B.
C.
Which one?
C, sir.
So if you increase temperature, definitely it will decrease in metal. Okay.
Yes.
And it will increase in intrinsic semiconductor. Okay, that's right.
And temperature coefficient of resistance.
Yeah, definitely. So the C is right. Okay.
Right.
The conductivity of a semiconductor due to any current carrier is not proportional to. Conductivity is not proportional to what? Mobility, effective density of states, electronic charge, surface states. Which is right? Which is not depending upon conductivity? See, we know conductivity equal to, suppose you take you take intensity, okay, it will equal to Q into Ni into mu n plus mu p, right na?
Surface.
Huh? Yeah, so it depends on charge, mobility. The Ni means Ni also depend upon the density of states na?
Yes. Yes.
So option D should be the answer, right? Okay.
Actually, what's the surface state actually? Because I
Surface
have
state
just
means
eliminated.
yeah, in a semiconductor, right? Semiconductor, okay. The bulk, right? Bulk is like very, you know, arranged regularly, atoms are arranged regularly, there is no defect, okay, all bonds are there. But in the surface, right, there is lot of broken bonds will be there, okay. Lot of broken bonds will be there. Surface is not very, arranged in a very systematic way. In the bulk, atoms are arranged very systematic way, but in the surface, right, surface, there will be a lot of bonds will be broken, lot of impurity will be there. Okay, so there will be lot of surface stress will be there. Reading? It's like
So
you see. Yeah,
actually,
tell me.
that does not contribute to conductivity, right?
Yes, I'm telling. That's why it is not proportional to surface states. Okay,
Okay.
I'm asking not what.
Okay. Okay. Yes. I
Then
have just actually eliminated D because A, B, and C are contributing.
okay, that's
So
right.
that's why I don't know this surface state. Right now I understood because you have explained it.
Okay, no problem. So now, what is the question? It is really disturbing here. This one
There is some bug.
coming like anything. I don't know how it is coming. Okay, we will do one thing. I will close this whiteboard. Okay, I will quit this whiteboard. Okay,
Okay.
now visual.
Clear, clear.
Okay, now okay. This you understood. Okay, this question you will do. Okay, this one. Okay, the electron mobility is given. Okay, mu is given. Mu is given. Okay, lifetime is given. Tau is given. Okay, we are asking what is diffusion length. Reading?
Okay.
Okay, who know uh, diffusion length is equal to root over of dp into tau p. Tau. Okay, getting?
Okay.
You understand? Diffusion length is diffusion length. Okay, diffusion length is okay. Average length after which they will the diffusion length. Okay, diffusion length LD. Okay, equal to root over of dp into tau p. Okay, or dp into d into t. You can say
From where we got that, right?
that how you got. I will explain in the next class. You make me recall. Okay, I will explain you. Okay,
Okay, okay.
timing now you understood that is dp into tau p. Okay, so you got tau. You know d for getting this diffusion length. Okay, so since you have mobility, okay, for mobility you can calculate the diffusivity, na?
Okay, okay.
How you tell me?
Earlier, I have derived from
Yeah, dp by p is equal to right, d by mu is equal to pt, right? You know mu, you know thermal voltage. I can know d, na,
yes, yes.
and I know only tau. So you put this in this formula, we will get the answer. Okay. Okay. The drift velocity of electron in silicon varies with the applied electric field in which manner. Okay. So I told you that the drift velocity, okay, it first increases linearly, then sublinearly, finally it attains a saturation. I told you, right? I explained you, na? Net flux is nothing but net velocity. Okay. So with electric field, are you getting what I'm telling?
Yes, sir.
Okay. I told you, na, see the net flux is equal to F1 minus F2. So the electric field will increase F1, will decrease F2. So after the F2 will almost be negligible, the net flux will be saturating.
Yes, yes.
It is nothing but flux is dependent upon the velocity. It is nothing but P into V1 minus V2 by 2. So if you see, if V1 will increase, V2 will decrease. If V2 will be approximately very less, then it will be saturating P into V1 only, right? Na?
Right.
Okay. So the depth velocity, okay, depth velocity. See, actually, this is not the case. Actually, this is a mistake I have done. Okay, let me tell you. Okay, so we know, okay, we know J drift, okay, sigma into E,
Okay.
right? So what is drift velocity? Drift velocity equal to E. Okay, this is my drift velocity. This is my this. Okay, now will equal to okay. So this is equal to Q mu P into Vd. Okay, so V drift velocity is nothing but okay. Sorry, equal to Q P into Vd. So Vd is nothing but mobility into electric field. Okay. Hello.
So actually, after sigma e, J drift equal to sigma e, then conductivity is formula is written
Pardon me. Huh.
QP
This is
mu
this is
P into
conductivity Q mu P in P. Okay. So QP I have calculated mu P into E is Vd. Okay.
yes, yes.
So this
Okay, okay.
Vd will increase if I plot Vd versus electric field. Okay. It will increase. Then after certain time, right, it will saturate. Okay. Because I told you, right, it will oppose the motion from another direction. When it will go to zero, it will saturate. Clear?
Okay, okay, okay.
Okay. So the same is nothing but F net equal to F1 minus F2. When F2 will be almost zero, it will saturate.
Right.
Right. So this is nothing but this is called velocity saturation. Okay.
Okay.
So for slow For lower electric field, okay, it is proportional to mobility. Okay, for lower electric field, it is proportional to VD and mu. For low electric field, okay, VD and electric field give the. So if you see VD and electric field, right, it will be like this. For lower electric field, right, the slope of VD and D will give mobility, right?
Yes.
But
Really.
for a higher electric field, right, this equation will not valid. When the velocity will saturate, right, this equation will not valid.
Okay.
Right?
Linear
So then you have to go to in this region, right? This equation is not valid. You have to go to some other equation.
Okay. Okay.
Ready?
Getting.
So this is called velocity saturation because it will oppose the other direction velocity up to almost zero. Okay. After that, net velocity will be almost constant. Ready?
Getting
So
it.
after this electric field, right? Even if we are putting electric field, okay, it is not increasing my net flux.
Okay.
Okay. So the velocity also saturates. Okay. So this is the this question.
Okay.
Oh, yeah. I think this much questions I have taken from this chapter. Okay. So I think next class we will start freshly the diode chapter. Okay.
Okay.
Okay. So till now there is no doubt, na?
No doubt.
Okay. So we'll start freshly the diode chapter in the next class.